Lastly, let us consider example 2, where we want to find the equivalent resistance of our circuit shown below. Now we have to recognize a few things before we proceed with finding our equivalents. We have to recognize that R1, R2, and R3 exist in a series configuration. That is, we could say R1 plus R2 plus R3 can be equal to an equivalent resistance REQ1. We also see that R4, R5, and R6 exist in a series configuration, and we can call this REQ2, where the equivalent resistance is the sum of the resistances of R4, R5, and R6. In doing such, we would have 4 resistors existing in a parallel configuration. That is, we can say 1 per R total would be 1 per REQ1, which was the sum of R1, R2, and R3, plus 1 over REQ2, which was the sum of R4, R5, and R6, plus 1 over R7 and 1 over R8. Expressing R total 1 as the parallel equivalents of REQ1 and REQ2 as follows, and R total 2 as the parallel equivalents of R7 and R8. We can then do the parallel equivalents of R total 1 and R total 2 to get the total resistance of our circuit network. That is, REQ would be equal to our total resistance, which is R total 1 times R total 2 per R total 1 plus R total 2. If we substitute in our original expressions in terms of REQ1 and REQ2 and R7 and R8, we'd have the right-hand side of our equation. Furthermore, you can substitute in R1 plus R2 plus R3 for REQ1 and R4 plus R5 plus R6 for REQ2. You can verify this via using conductances.